Hi, guys. Um, well, you're watching me on a recording for 2.6, Math 25 2.6 on rational functions instead of seeing me live. And that's okay. It's just a different environment. And you'll have about an hour's worth of my lecturing this way. And let's take a look and see what it's all about. A rational function, you can take a look here and you know what a function's all about. Function definition, formal definition is for every x value, there's only one y value, or a picture that passes the vertical line test is called a function. To be rational, it has this form, which is a fraction. All rational numbers are fractions. Yes, all rational numbers are fractions. These are polynomials, which you're going to find for these functions. A rational function is the ratio of two polynomial functions. For instance, this may not look like, when I zoom in here, a polynomial function in the numerator, but it is. It's a polynomial of degree 0 because there's no variable. It's a degree 0 polynomial. This one's a polynomial of degree 1 because there's a degree right here of 1. When we look at fractional values or fractional functions, there is a domain issue possibly. And if you recall in your packet, I said the domain of any function is all real numbers unless you see fractions, roots, logs, fractions. So I see a fraction. So when I take a look at this, you can't use a number that would cause the denominator to be 0. -1. -1 plus 1 makes the denominator 0. So you can't be asked, if I said, what's f of -1? You would say 1 over -1 plus 1 equals 1 over 0. And you say, that's undefined. You can't use that. So when it talks about the domain, find the domain, it's all real numbers except that number -1. So the domain, D for domain, would be variable x. So it's all real numbers. This is set building notation. All real numbers. X just can't be -1. And if you wanted to write that domain in interval notation, you exclude -1. So you have from -infinity to -1, and then union -1 to infinity. That would be the domain. At this point right here, let's not worry about this approaches right here. Don't worry about that. So what happens is on the picture though, the thing that you can't use, which is -1, turns out in the graph, a very obvious issue. Here, I'll show you with the graphing calculator. I'll show you. So when I put this in the graphing calculator, that equation right there, so that was 1 over x plus 1. I do zoom standard. And as you can see, there's a gap. See how that's making a turn? There's a gap. That's called a vertical asymptote when you see a gap that looks like this. Called the vertical asymptote. And you'll be asked for some of the problems, what, if any, are the vertical asymptotes? It's where the function is undefined, meaning where there's a problem in the denominator. And the problem is at -1. So down here, you'd say the vertical asymptote is x equals -1. Now, this whole thing about a horizontal asymptote, we're going to find out what that's about on the next page. And this general statement that's down here, this is something about calculus with its limits. Don't worry about it. It might intimidate you, but you're going to see it in your 1A class when you get there. But that's still, for most of you, a year away, because you probably still have to do your Math 58 after this. So the point is, this is a rational function. Sometimes you have places where it's undefined. Those are called vertical asymptotes. And the equation of the line, which is this is a vertical line. That's a vertical line. And now we're going to look at some other asymptotic behaviors. And those are called horizontal asymptotes, horizontal lines. Now, horizontal lines equations are y equals. Horizontal line y equals a constant. Vertical lines are x equals. You might start thinking, it's going up and down. That's a y-axis. No, the equation of the line that's vertical is x equals. The equation of the line that goes horizontal is a y equals. Don't think about the axis at all. This big, scary function equation right there, it's in your textbook as well. Basically, it's saying you got a polynomial at the top, polynomial, and there's a degree n at the top, n. It's in descending order of power. And down below, just to have a different letter, that's a degree m. Sometimes they're different, the powers, the degrees, and sometimes they're the same. And that's what we're going to look at. So the first one, okay, n, think n is numerator. So if the degree in the numerator is smaller than the degree in the denominator, the degree in the numerator is smaller than the degree of the denominator, then it turns out y equals 0 is your horizontal asymptote. What's a horizontal asymptote? Well, it looks like this. Here's your y, here's your x. Here's your horizontal asymptote at y equals 0. I'll put it kind of right on top of the x-axis, y equals 0. That's what it would look like. So the picture for this would have some behavior along the line somewhere. The degree of the top right here is 1. The degree of the bottom here is 2. So the degree of the power of the polynomial in the numerator is smaller right here than the degree in the denominator, which is, they call it q of x. All right, now these are identically the same. See how the degrees are the same? If the degrees are identically the same, there is a horizontal asymptote, and it looks like y equals something. Y equals something. So the horizontal asymptote would be y equals, okay, now the a sub n and b sub m, they're the numerical coefficients in front of the, well, in this case, the squared term, the numerical coefficients. 4 over 2. So this would be 4 divided by 2. So the ratio of leading coefficients, 4 over 2, or 2, is the what they call the horizontal asymptote. Y equals 2 is the horizontal asymptote. So on this one, if this is your y-axis, this would be your y equals 2 horizontal asymptote. Now I'm going to show you what this one looks like in your calculator. In graphing this one right here, clear that out. Let's see, make a little fraction like I've done before. 4x squared, then 2x squared, and then plus 1. Graph. See, it's kind of looking like, you see how there's a, it looks like a line, like goes this way. That's that line right there. It's called an asymptote. There's some behavior with regards to that. There's an asymptote that goes like this. And the last scenario is, what if the numerator is bigger, not the same, not smaller, but bigger than the denominator power? And if it looks like this, there is no horizontal asymptote, none. So this page that I've just done is all about horizontal asymptotes. The degree of p of x is 3. The degree of q of x, which is down here, is 2. This one is p of x. This one is q of x. No horizontal asymptote on this one. So right now I've shown you vertical asymptotes. Vertical asymptotes. Okay, look at this. If I were to ask about a vertical asymptote right here, I'd be saying, well, what value of x would make that into a 0? Or 2x squared plus 1. I wonder what makes that a 0. Well, if you solve it, that's what you're asking for. Well, here's a problem on this one. It's not really a problem. It's just here's what's going to happen. When I solve for x squared, I get x squared equals -1/2. And then when you multiply, no, actually not multiply, but when you take the square root of both sides, you're going to take the square root of a negative number, and that's imaginary. And asymptotes are not imaginary. You actually see them. So this one doesn't have vertical asymptotes, unlike the other one, the first one we did, which -1 caused the denominator to be 0. Okay. Now, slant asymptotes. Okay, that's the other thing that we want to take a look at. So slant asymptotes use long divisions to figure out what the slant asymptote is. And it turns out that when you do the long division, the dividend, the result, which should be the quotient actually, the quotient is, without the remainder, is the equation of the slant asymptote. Say that again. If I did long division on this, which is 2x squared plus 1 into 4x cubed, don't forget you have to go 0x squared and 0x and then plus 0. 2x squared to make 4x cubed, you go a 2 and an x. That would be 4x cubed, and then plus 2x. Subtract, goes away, bring it down right here, -2x. And now we're done because that's going to be the remainder. So it turns out that this right here, the equation of the line, y equals 2x, is what they call the slant asymptote. And if you graph this by, that's y equals mx plus b, the slope-intercept form. So the y-intercept is 0 because I don't see a b. So if I went here, and then I did the slope, which is 2 over 1. 2 over 1. So I went up 1, 2, and then right 1, and then did a dotted because that's called a slant asymptote. You'll see by the picture of this that the behavior wraps around this line. There's like asymptotic or symmetry. So if I graph this one, and I make that power into a 3, it looks like, and then hit the graph. Oh, you see how it's wrapping around that line? There's actually a little dip in there, but it looks like it's wrapping around that line. That is the equation of the slant asymptote, which is y equals 2x. So this is your slant asymptote. So we got slant asymptotes, you got horizontal asymptotes, you got vertical asymptotes. Now, the only other thing in this section that will be new is what we call holes. Now, holes occur when the numerator polynomial factors and the denominator polynomial, let's say, factors, and a factor goes away, which will make likely a vertical asymptote disappear because you're making one of the top, the thing in the bottom goes away. But it doesn't really go away because you still can't use whatever caused it to be undefined to begin with. Here, I'll show you what I mean. This one here, if you factor this, I can't use 1 because that'll make that into a 0. So you can't use a 1, that'll make it into a 0. And I can't use -1 because that'll make that into a 0. So x can't equal 1 and x can't equal -1. It turns out if I ask you for what's the vertical asymptote, you'd say x equals 1, x equals -1. There's two vertical asymptotes. However, when something like this happens and you make it go away and reduce it down to 1 over x plus 1, it looks like for this one, x equals -1 is still a vertical asymptote, but you can't use those. But if you said, what about this one? X equals 1. Instead of it being a vertical asymptote, it's now a hole. It's now a hole. So here's what it's going to look like by hand a little bit, and then I'll show you by the calculator. Okay, so a vertical asymptote, vertical line, dot, 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 that goes through, in this case, -1. So this one here, vertical asymptote, so you'll see a gap in the picture. With it being a hole at, say, 1 right here, somewhere along here, there's a hole. And I'm not quite sure where it is yet until I graph it and show you. So I'm going to graph the original right here. Graph the original. Zoom standard, okay. Well, there's the gap right there. And the question is, there's a hole somewhere. So wherever 1 is, there's a hole. How do you know, Jeff? Well, watch. When I do a table of values, second table of values, and I'm looking for 1, it says there's an error. There's an error at -1 because it's a vertical asymptote. You can't use it. But there's also an error at 1. So what you'll do is, that's the number 1. That's not a vertical asymptote. It looked like the picture right here. Right here, there's a hole right there. There's a hole. So it'd probably go like this, hole here. And then the picture looks like it's coming down. Like that. So it's coming down, and then it continues to be above the x-axis, because there's a horizontal asymptote. Remember that? If the degree at the top is smaller than the degree at the bottom, there's a horizontal asymptote of y equals 0. That's this one here. That's the horizontal asymptote at y equals 0. And then there's a hole. There's a hole right there. They just don't show it on the calculator because it's so small. Hole so small. And then this picture right here on the left-hand side, you can sketch that in like that. And that would be a sketch of the. So this is a vertical asymptote. Then you'd say that's a hole, and then the horizontal asymptote would be y equals 0. Y equals 0. Okay, these should be familiar because it's basically the transformations, and you're comparing it with this base function, 1 over x, and there's always an order. Order is important. You go left, right first, reflect or vertical shrink and stretch second and third, and the last thing would be the up and down. This one here is a right, because you always go opposite of what's inside the argument. So this is a right 2. This is a left 3. This is an up 4. This is a down 5. There's a negative, so this is a reflect. So reflect about, I need this, the x-axis. Reflect about the x-axis. And this one has 2 steps. So you do the left, right first. So that would be a left 1. So this would be a left 1. And 2, that would be a down 7. So as a reminder, we've seen those before in different functions. Okay, the rest of these are a variety of examples. I think I'll do 3. I'll take a look at 3 of these. I've got more than that, but 3 right now. I'll do the first one here. I'm asking questions that we probably will find most of them with our graphing calculator, so I might as well go ahead and graph it first. So taking my calculator, and I'll graph this one. Now, my eyeballs are going a couple things. First of all, there's a denominator, so there's going to be a vertical asymptote unless the top can factor. So that's what I would try doing, this factoring. Now, the only factors I can see is 2 and 4, or 1 and 8, and it's not going to give you the 5. It's just not going to factor. So there's not going to be a hole because a factor would have to have an x plus 3 up above to make the x plus 3 down below go away. So there's no factors that will make the vertical asymptote into a hole. So right now, the vertical asymptote, I can even, before I even graph this thing, the vertical asymptote would be x equals -3. It's always the opposite of this to make it into 0 in the denominator. Okay, but we'll take a look at the picture. See, -3 is right here. That's a vertical asymptote. Okay, that's a visual confirmation. Look at this. This looks like there's a slant to it. So there's going to be a slant asymptote. Sure enough, if the degree at the top is 1 more than the degree at the bottom, there's a slant asymptote. So how do you find the slant asymptote? Long division. Oh, okay. So let's do the long division maybe up here. You got x plus 3 . Okay, multiply by x squared plus 3x, subtract 2x plus 8, and then make this a 2x, you go plus 2. That would be 2x plus 6, subtract. Okay, now there's going to be a remainder, but you ignore the remainder. That's my instructions say that too. You ignore the remainder. This result right here is the equation of your slant asymptote, but you need a y equals. It's the equation of a line. So down here, you'd say it's y equals x plus 2. That's the equation of the slant asymptote, which if I look at this, the equation of the slant asymptote is right here. Oh, you don't believe me? Here we go. Let's put the equation in x plus 2 and graph both of them. See, the equation of the slant asymptote, it worked. Okay, what else? Oh, horizontal asymptote. Now, if the degree at the top is bigger than the degree at the bottom, over here, the degree at the top, if the degree at the top, the numerator, is bigger than the one at the bottom, there is no horizontal asymptote. So all I have to do is say none or no. Okay, the y-intercept, let's go up here. Yeah, it doesn't look like it. The curve doesn't look like it. Cross, oh, my mistake. The curve does cross up here. Let's get rid of this right here. Let's get rid of that. Yeah, the y-intercept is right there. And how to find it, you would end up letting x be 0. So if the y-intercept, you go x is equal to 0, then everything here is 0 except 8/3. So the y-intercept is 0, 8/3, which is almost 3. If you look at this, that's almost 3. The x-intercept doesn't cross the x-axis, so you'd say none. Okay, relative minimum maximums. Okay, you find those by the terms. Okay, there's a relative maximum right there. Remember, it's a y value, so if I go second calc maximum. Now, I'm hoping for this. I answered the question. I want the left bound. So pick something over here, like -9. And we see a flag over there. Now the right bound, you got to be careful. You don't want to go past the wall, which is at -3. You don't want to go past it. You don't want to go over here. You want to stay on the left-hand side of the wall. So stay on the left-hand side of -3, like -3.5, maybe, -3.5. And then hit enter. And looks like we get the Y. Now this is the Y, this is the minimum value. It's always, or excuse me, maximum values. That's always the Y value. So what you're going to do is relative maximum is Y squiggle squiggle -3 point, let's say 83, 3 decimal places. And then you do it also for the minimum value. So we do this all over again, second calc, but we do minimum because it's a valley right here. Here's my minimum value. So don't look at the cursor, look at the question. Left bound. Now I can't go past that wall. I want to be the left of that orange dot. I don't want to be over here because I just passed the wall. I want to be on this side of that wall. So how about, let's see, that's -1, -2, that's -3. So how about -2.5, -2.5. And then right bound, I can be anywhere over here, which is maybe 6, and then hit enter. And then you can see the asterisk is at the lowest part. So you go Y squiggle squiggle 1.83. The domain would be all real numbers except where it's undefined. So let's see. I can't use -3. That's the vertical asymptote. I can't use -3. So if I say the domain, you'd say -infinity to -3 union -3 to infinity. And the range is how low to how high. The range is how low. Okay, so -infinity up to here. And then you start over again. You can't see that. So -infinity up to here. And then you jump up here to the minimum up to infinity. So -infinity up to this Y, looks like it's a maximum, relative maximum. -infinity up to the relative maximum, which is -3.83. In union, now we start again right there where the cursor is, which is at 1.83, all the way up to infinity. Because it goes up to infinity, either that way or that way, up to infinity. So not easy, different kind of topics. This is going to be a big section for you guys, big section. Okay. Now the thing about this one, I'm not going to do this one because I'm just going to identify that there's a hole. It doesn't list a hole here, but is there a hole? Hole. If you factor this, then those go away. And what used to be a vertical asymptote, x equals 1 is a problem, is now a hole. That's not a vertical asymptote now. It's called a hole. And if it's a hole, and what's left here is x plus 2. So g of x is a fancy way of saying y. So you're going to have an equation that really looks like a line. And at 1, there's going to be a hole. At x equals 1, there will not be a vertical asymptote. It's going to be a hole. And the rest of these could be answered accordingly. All right, fine. You want to see that? I'll put this in my calculator. The ultimate result's going to look like that because the factors go away. It looks like a line. Looks like a line. Looks like this right here. But at 1 right here, there's a hole right there. There's a hole. And how do I know? Watch what happens when I do a table. It'll say error right there. It says error. And then other questions you guys can easily answer. Is there an x-intercept? Yes. What is it? You can find that. Is there a y-intercept? Yes. Can you find it? You should be able to. Is there a horizontal asymptote? Doesn't look like it, because horizontal asymptote means there's something that passes this way. Besides, the degree at the top is what they call bigger than the degree at the bottom. So no horizontal asymptote. Relative mins and maxes, there's no turns, so none of those. What's the domain? Well, you can't use 1. You still can't use 1 because it's a hole. You can't use 1. So the domain would be all real numbers. You can't use 1. And the range, okay, the range is from lower to higher, negative infinity until you get right here, wherever that is, all the way up to infinity. So if I put a 1 in here, it looks like it's going to be 3. If I put a 1 right here, it looks like it's 3, but there's a hole. So for the range, you can't get 3. You would say it's all real numbers. Y just can't end up being 3. Let's see if I can do another one here. Yeah, let's do this one here. Okay, now, when I'm looking at the denominator, that's where the vertical asymptotes exist. So what you'll do is you go 3x squared, subtract 9. You wonder where the vertical asymptote. So solve for x squared. 9 over 3. So x squared equals 3. All right, then you want to take the square root of both sides. So when you take the square root of both sides, you have x equals plus or minus the square root of 3. Those are called your vertical asymptotes. Vertical asymptotes would be x equals root 3, x equals negative root 3. Y-intercept is simply let x be 0 and solve for the rest of it. As x is 0, you've got 0 over negative 9. Like 0 over negative 9 is 0. So the y-intercept is, well, gosh, when x is 0, y is 0. Well, that's the same as the x-intercept. Is there a horizontal asymptote? Well, the degrees are the same. According to the instructions, if the degrees are the same right here, then the equation is a horizontal asymptote. It's y equals the ratio between the leading coefficients. So since the degrees are the same, 2 over 3 is the horizontal asymptote. Y equals 2 over 3. Is there a slant asymptote? You probably figured that out. If there's a slant asymptote, there's no horizontal. If there's a horizontal asymptote, there's no slant. You can't have both. So no slant. Is there a relative minimum value? Well, I don't know. I have to look at my calculator. Put this in my calculator. Zoom standard. Relative maximum there. That looks like a 0. Relative maximum there. Now it's a y equals 0. Now the relative minimum, there has to be a turn. This does not turn back up. It doesn't turn back up that there's a distinctive, let's say, turn. It just keeps falling, going this way. So there is no relative minimums, none. None. Okay, what about the domain? Well, you could use everything, but what makes the denominator 0? Oh, I can't use those. So I could use the domain would be all x is such that it's real. X just can't be plus or minus root 3. And now the range. The range is low to high. Low to high. So range, negative infinity, up to here, which looks like it's a 0. And then you pick back up here at 0, and then you continue on forever. So it looks like I'd have down here, for range, you have negative infinity up to 0 bracket, because you actually get it, union, and then you start over again at 0 comma infinity. But because I use it here and I didn't there, I get everything anyway. So really it looks like it's all real numbers. So those are 3 good examples that the author does about 3 or 4 as well. Yeah, I won't do this one. Yeah, I think those other ones are good. They don't need to be done because you've got enough examples in your textbook. I will do one of these though. Now these go backwards. These are asking you to create the function that has conditions, where the other ones I just did, they give you the function and ask you, what are the conditions? I'll say it again. This one here gives you the conditions. It says, what's the function? So it's like working backwards. So I'll do this one here. So what we're going to do is you're going to find an equation of a rational function. So you say, let's say it's g of x. And it's rational, so there's a fraction. So first of all, vertical asymptotes. If x equals 3, if x equals 3 is a vertical asymptote, you rewrote it as x subtract 3 equals 0. That is the piece that goes right here. Think about it. If your vertical asymptotes are found in your denominator, and you found out x equals 3 is the vertical asymptote, well, it's just working backwards. So check. To have a horizontal asymptote of y equals 0, you have to have the degree at the top be less than the degree at the bottom. Okay, that right there is 1. So the only way that I can have this right here so far is that if the degree is 0, which means there's got to be a constant. Let's see. So let's see. Y-intercept of -1. If I let x be 0 to find the y-intercept, that's a 1, by the way, not a power of 2. You might think it's a power of 2, but I made it into a 1. Come on. That's x minus 3. So to make, if I let x be 0, I need this to be -1. I need it. So how about if I make this a 3? So when x is 0, you have 3 over -3, which is -1. So that takes care of this. No x-intercepts. Take a look at the graph and you'll find out that there are no x-intercepts. And so you think that this is the answer. Let's take a look and see if that's true. No x-intercepts. Let's see if I've found the function. Any x-intercepts? No, 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 no. No, no x-intercepts. So I found it. That would be your function. Those are hard to do because it's like thinking backwards or working backwards. Okay. So this is similar. I'll let you take a look at it. The author has a couple of those as well. So I think I'm done at this stage. Let me unshare my screen. And to let you know, if you've got any questions, seek me out, email me. Now, the day that you're going to get this, I'm actually indisposed. The day that you're going to get this particular one, it looks like on the 20th. On the 20th. So on the 20th, what is it? The 22nd, that's a Thursday, you get a group quiz to work on. So hopefully this makes some sense. And seek out Bonnie. Bonnie's going to be in her study session, but seek out Bonnie if you've got any questions. Okay, well, next time, see you later.